All right, welcome everybody to the afternoon session. First talk is Eric Michaud, MIT, the quantization model of neural scaling.
Thanks. Yeah. So this was a preprint that we put out a few months ago, and kind of like central question that we're wrestling with here is, how does scaling change what neural networks learn? How are big networks different from small ones? In particular, like what would be a way of thinking about the effect that scale has on what networks learn that would make us more optimistic about doing mechanistic interpretability even on very large networks? And like any kind of story of neural scaling has to wrestle with a couple of things. So first, it has to like wrestle with the fact that there are these scaling laws, which we know about. And in general, this like predictability of the like aggregate performance of the models as a function of parameters and data size and this sort of thing. And also sort of like maybe ideally have something to say about sort of emergent abilities of the models. When we look at very particular tasks, right, there's sort of curves where like small models maybe don't seem to do it at all, and then at a certain scale, the model is able to do these like very particular things. But on other tasks, like it seems like scaling is more gradual. So like, is there anything we can say about emergence and the difference between things that improve gradually versus that spike at certain scales? And in general, like, is there some resolution to maybe this sort of conflicting facts about scaling, where like on the one hand, in the aggregate, things look very smooth and predictable, and then maybe when we zoom in, things look a little bit less smooth and predictable. And so here's one possible story of scaling that we conjecture. So maybe there are just like, for your given learning problem, language modeling or something, maybe there are just like a bunch of things which you need to learn to do prediction well. And we're further going to sort of model these as being discrete. Either you sort of learn them or you don't. And we're going to call these the like quanta of the problem. And in general, like the title of this stuff in terms of quantization just like refers to this like assumption of discreteness that we're making about what can be learned and what is learned. And then number two, we're going to say that some of these things, these quanta, are really more useful for prediction in the sense that they lower mean loss more than others. So if you can only learn so many, you should learn the ones that reduce the loss by the most. And so we can sort of imagine ordering these things according to how much they reduce the loss. We're just going to call that like the quanta sequence, the Q sequence. We're going to say that the effect of scaling is to just learn more of these things. And then lastly, we're going to say that the frequencies, I wish the quanta are useful in doing prediction, follow a power law. And that's an important assumption. And then, just to see how this can lead to power law scaling and the mean loss. Yep.
Are these like importance and slots internal similar concepts?
Yeah, maybe. Yeah, I think like ultimately the loss will decompose as like a sum, which will be weighted by the frequency here. And like if the frequencies follow power law, I think that would be the same as the importance following the power law. Yeah.
Are we assuming that the quantas are all independent? Like there might be quantas like that depend on other quantas being learned earlier. And
yeah, I'm going to assume they're independent, but like that feels unrealistic. Like maybe there's a kind of skill tree thing going on in reality. Yeah.
But I would have thought that importance is like this ranking of the different quanta as opposed to their frequencies. I don't think importance is the same thing as how often.
Like, so here I'm going to say that like the frequency like drives the order.
So they're the same.
Yeah, like
You could talk about frequency and order interchangeably.
yeah, like this actually is kind of maybe more implying this than
Okay.
being independent or something. But anyway, like we can model how this like can lead to power law scaling in the following way. So like we're just going to say that everything is either like everything in the sequence is either learned or it's not. So we can just like represent like what the network has learned as this like very big binary string. Where if like the kth bit is like on, then the network has learned that quantum of predictability. And then we're going to say that, well, like things are going to be learned in order from number two. So like if we learn n of these quanta, then like we're going to learn the first n. And so like really we can imagine like our model's performance is just depending on n, the number of quanta learned. We're just going to learn the n before. Then when he says that, we K quantum benefits prediction on a fraction piece of K of samples where a piece of K follows a power law. And this can lead to power law scaling like so. So if we assume that like learning each one of these things reduces loss on the samples where it is used for prediction by some constant amount, like let's say that it reduces loss from B to A or something, and the amount it reduces loss by is B minus A, then you can like imagine writing the loss, grouping together samples according to like which quantum they rely on, as this big sum over samples where you've like learned the thing that you've needed to learn to do prediction, plus like term for samples where you haven't learned the thing that you need to do, or you need to learn to do prediction. And this is going to be then weighted by those frequencies. Here, like L is like the mean loss. And you can basically rearrange this and approximate with an integral, and you get that the loss is a function of n, number of quanta learned, is a power law in n, where the like scaling exponent alpha is like related to the power law distribution exponent over the frequencies. So that's like a power law in like number of quanta learned, but like how does that translate into a power law in like number of parameters or number of data points? You can come up with stories for this. So like maybe each of these things, these quanta like requires the same, or it could be modeled as like using the same number of model parameters or something, like it requires the same capacity. And if like the number of quanta then is like proportional to the number of parameters, then like you get power law scaling in number of parameters. Here, basically, as we just increase parameters, we have like the capacity to learn more and more of these things, and we can translate into a power law in n. We can also have a power law in D, the number of data points in the training set, where like one assumption you can make, for instance, is maybe there's just some threshold number of samples requiring that quantum like needed in the training set in order to learn it. And then sort of roughly for each of these things, then you'll have B times P sub K, like samples requiring it in your training set. And then you might ask like, well, how large does D need to be to learn the nth quantum? It's just like whether D times Pn is like greater than or equal to tau, and basically you can solve that and you get a power law in D, where the exponent is like a little bit different from just alpha as a small correction. You can also come up with a story for scaling in training time. So like maybe the gradients for learning the early quanta and Q sequence are, they also might follow power law or something, because like the amount that you reduce the mean loss by in learning them follows the power law. And so like maybe the rate at which you'll learn them will also follow power law. A little bit hand wavy, but you can basically come up with like a similar type of story for training time, where like the amount of steps that it takes to sort of like learn the nth quanta, like follows this kind of power law, and then plugging this into the power law, you get power law in training time. So basically we can, using this assumption of this power law distribution over the frequencies that these things are useful for prediction, we sort of get these power laws in the mean loss and things like parameters and data, making certain assumptions about like what having more parameters allows you to learn more quanta. So now I'll just say that it's possible to construct data sets where this kind of story is true. So what we did was we took the sparse parity task, where it's basically just a binary classification problem on binary strings. You choose some subset of indices ahead of time, which you're going to compute the parity from. And so like the answer to the classification problem is just the parities of sum mod 2 of that subset of bits. So during training, the network needs to like figure out which subset of bits it's going to like compute the parity from. And learning curves for this look like these kind of reverse S-shaped curves, sort of phase stream type curves. You can basically just
What would the stop halfway? What's the red?
I'm not sure. So this figure was from this paper describing this was studying this problem, and like basically showing that like, in many things, but like that a bunch of very simple like architectures can learn how to do this. But I'm not sure like, like step. Yeah. It's tempting.
Therefore, you start working like a food.
Oh. Okay, so it's possible that like the way that the network was maybe solving this is that you need to like learn a feature for like each combination of like the relevant bits. So like 0, 0, 0, you need to like learn a feature which like activates when that is present in the relevant bits. And like having that allows you to get right the samples for which like are 0, 0, 0. But then you like need to learn other features for each combination. Here you need to learn like 8 features for the 3. So maybe that's like the partial progress that you're seeing, is that like the problem of like doing this is like not super like unified, but like itself consists of more like basic discrete things of like these 8 features that you need to learn.
You know how many parameters these networks have?
I think pretty small. I'm not sure what like what's going on with this figure exactly. It's mostly just illustrating like the way that these learning curves look. But I think like a variety of sizes of networks. But you can do it with a one hidden layer ReLU network. So, and I hear that these can be understood theoretically in various ways. So it'd be interesting to look at that. But you can make this kind of multitask problem where I'm just going to add bits to the input, which are going to like specify which subset of the bits from what we call the task bits the network is like supposed to compute parity from. So like, and we do this in this one hot way. So like if the first control bit is on, none of the other ones are on, then like that means, and you just like ahead of time you choose them randomly, that like the network is supposed to compute parity from a particular subset, and then a different subset for a different control bit being on. And then all I do is I impose a power law distribution over like how frequently the control bits are on. So like most frequently, the first one is on, and less frequently the second one is on, and like the frequencies follow power law. And then these are uniformly distributed, the task bits. And what you get when you train on this is a curve where like the mean loss averages over lots of these more interesting looking learning curves when you look at the model's performance on subsets of the data. So like each one of these curves is a mean across samples where a particular control bit was on. So like maybe the first one here was like a mean across samples where the first control bit is on, and so on. And they sort of converge at different times. And like overall, your loss curve is averaging over lots of these interesting looking learning curves. Yeah.
Is this more single seed? Or is it average over?
I think this is a single seed. Yeah. And the story of scaling is pretty cool because what happens, so here, the top row, I'm showing mean loss across like the whole data distribution as a function of parameters. So here I was just training a single hidden layer ReLU network, so I was increasing the width of the hidden layer. And we sort of roughly get this power law. Also in training time and number of training samples when you're doing multi-epoch training. And the cool thing is just that these scaling laws are like averaging over this kind of like discrete thing where the network is getting zero loss on like a larger and larger number of the subtasks.
Is the alpha in the scaling law in the picture, the alpha where you distribute your control bits?
Oh yeah, so I'm plotting the line there. So yeah.
It's not a best fit, right? It's from the alpha.
Yeah. Right. So it kind of is not a very good fit for the scaling in time.
Okay.
These are like a little bit steeper than I would expect theoretically for some reason.
Right.
And also this is like I have a little bit more to say about this, which is that like the relationship between the like chosen alpha for the frequencies is like its relationship to the empirical scaling exponents on this task is like a little bit messier than I would have thought. So like here we're showing scaling curves for a bunch of different alpha. I'm measuring the scaling exponent for each one. And then I'm plotting the distribution over the subtasks, like that alpha versus like the measured empirical like scaling exponent. And like the black line is like what I would expect from the model that I described. And like it's not exactly on the line. These are all a bit steeper for scaling in time. And then like, I don't know, this is really shallow for scaling in data. So like, you know, it's not like this is exactly maybe following like the model, but like at least it's the case that like scaling overall is like averaging over a large number of these like qualitative changes once you like really decompose the performance of the model. Yeah.
When you vary one of them, do you make sure that the other two are definitely not bottlenecks?
Oh, yeah. So here I was training on like infinite data for scaling parameters. And then when I was studying data
And
scaling
with infinite time as well. Yeah, and the data, yeah.
for time, like maybe here.
So like just in case like maybe something else is one of the limiting factors with the other things is getting in the way.
Yeah, it could be, especially with like if the well. Yeah, like I tried to like make it long enough. So I guess maybe one factor with the parameter scaling is it's possible that like maybe if I had trained for longer or something, then like things would have been nicer. So it's possible I wasn't trained in convergence and that would have messed the payments. Yeah.
Are you implying that scaling exponents in just the single task sparse parity setup, it does match theory quite well? Because I mean, you just kind of, I'm just wondering if I missed a slide on this original one. So this is like not multitask. And
Yeah,
what
they
is the
I think that they were not studying scaling here. And I think that like even with a very small network, you get like basically zero loss. Like as long as you're like big enough to learn it, then you just like learn it, and then there's not really much scaling.
I see. Okay.
Yeah.
By the way, I just want to say I looked up that image, and what was going on in the image is multiple different SGDs on the same initial seed, each color is a different seed, and all they had to say about it was the time it takes depends a lot on the seed. So it doesn't seem that interesting. At least they didn't say anything interesting about it.
Why are they not all identical if they use the same seed?
Because they do SGD differently after that. The same,
It's like
sorry,
different
same
data order or
initialization.
something.
Sorry,
but-
same initialization, not necessarily the same seed. Yeah.
Okay, gotcha. Okay, great. Yeah, so anyway, that's like kind of a cute little toy data set. But you might wonder just in general, like, is this at all probably right for like actual language modeling? Like, might it have this kind of discrete structure? So in here, if you looked at like a particular sample, a particular like binary string as an input, I mean, here each little point like corresponds to a mean across like a bunch of samples that like have the same control bit on it. But roughly like what you would see is like that the networks would not do well on that sample like below a certain scale, and then like roughly above a certain scale they would like get approximately zero loss on them. So like everything looks like very kind of like step-like in the loss, but you know, is this actually what happens when you look at language model scaling curves? So what I did was I took the models in the Pythia sequence from Luther, and basically this is just a set of language models of varying size trained on the pile, trained on the same amount of data. So the only thing we're varying here is the size of the network. And I just evaluated their loss on like a large number of tokens from the test set of the pile. So I'm looking here at the loss on like an individual token, predicting it from its context from a document in the pile. And you just see when you look at these that like there are lots of different like scaling curves on individual examples. So like you can find scaling curves which look like it's kind of like plateau and then drop. Like here, this corresponds to like predicting part of someone's name, some politician's name, and like this corresponds to like predicting like the first letter and like the name of the company that this person works for. Is kind of like knowledge-based things. But you can also find like scaling curves which like look much smoother. So it's just not the case that like everything looks super discrete and like smoothness in the mean is averaging over a bunch of discrete things. So I guess like if we're going to believe in the kind of quantization model that I described earlier, like the presence of like lots of partial progress would like maybe suggest that what's going on is that like the network is benefiting from like lots of these quanta additively or something. But it's also possible that like the model is totally like not applicable to language modeling. But the interpretability like implications are kind of interesting because like maybe there are like lots of circuits which are like independently contributing to like lowering the loss, and like maybe understanding the model performance would involve enumerating lots of things, even on understanding its prediction on an individual sample. Yeah.
Yeah, another hypothesis is that it does have the quanta, but like it hasn't expanded the quanta to like different parts of the data set yet. Like the generalization of the particular what's it called, skill is off for whatever reason. It'd be interesting to test whether or not that like rule out that hypothesis.
Yeah. Yeah, like maybe there's like some computation which is present in the model, but like it just hasn't.
Like it could be able
Yeah.
to do it if it had, like, it needs to decide which of these skills it wants to use at any given moment. And it may not know when to use a particular skill. And the percentage of time in which it like the percentage of the data points which use that skill may expand or contract over time. And then this
Yeah.
would lead to continuous effects.
Yeah. I guess we kind of were like assuming this like very strong kind of like universality thing where like like the small model has the circuit and like it's the same circuit or something as in the small model as the big model, but like and then maybe it would like always be activated or something on the same inputs, but like maybe that's unrealistic, and like the way networks are like learning each of these things is that there's like not strong universality, and like yeah, could be contributing to this kind of knowledge. So, yeah.
Polygenic tokens could be produced by, in the scenario where like these individual tokens do not correspond one-to-one to individual quanta, but there's like a broad ensemble of underlying patterns, which these tokens are many different patterns. The model is like learning various quanta associated with all the different contexts in which that could appear, and then there's progress curves. Yeah, progress curves there, we represent learning many quanta that are like kind of relevant to talking about any of the numerous situations in which the word normal
Yeah.
appears.
Yeah, I think that's like a good like story of like what we would like to say about maybe what's going on with polygenic problems. But yeah, I don't know like if this is like the right framework for thinking about language models or not. But one cool thing we did in the paper, I think this is kind of like the last result in the paper that I'll talk about, was we just tried to like discover what some of these are. So like, can we, for instance, like partition like maybe 4 samples which are monogenic? Can we like cluster them based on like what computation or like behavior, capability doing prediction on those tokens relies on? So what we ended up doing is basically just taking the smallest language model we had from the Quantization sequence, getting a bunch of samples which the model got really low loss on. We did some additional filtering to try and get rid of some like induction type tokens where like maybe it's too easy to do prediction on those based just on the context. And we just did spectral clustering with the model gradients. So we were trying to cluster samples together based on whether the gradient was like pointed in roughly a similar direction. And what you get is many like seemingly quite meaningful clusters. So like here, all of these samples involve predicting a number. It's kind of hard to see probably, but like they involve predicting a number which continues like a numerical sequence. So it's like chapter 6, chapter 7, chapter 8, F3, F4, F5. This is in hex 0E4, 0F. And here it's predicting a new line, and it's predicting a new line in contexts where like the line length is limited. So like in code or in like other situations like OCR legal documents or something. Basically like you predict a new line to maintain it with text. So there's like maybe this circuit or something in the model that is like counting the length of the lines and then predicting a new line to maintain that. It's just really cool that this shows up in the gradients, because like this is like what is in common about all of these problems is like this like abstract like thing you need to know how to do prediction. which is not like simply a matter of like bag of words, statistical correlation, whatever on the input, but like maybe the gradients are similar because like the model is using some interesting unified circuit to do prediction on all of these or something.
How cherry picked are these?
These are the most interesting ones. Like I think how noisy things are depends a little bit on like the loss threshold I would expect. Like if things have really low loss, then like maybe there's like a very particular like reason that the model is able to like do prediction well on that, and like it's more likely to be like monogenic and less noisy.
But on a like high loss gradient cluster, you will find that pretty much everything in that cluster is sensible. Like
With
provided the
low
direction
loss
is similar.
cluster?
Like if the direction is similar and it's a high gradient, you will always find that the things in your cluster are sensible.
I'm not sure. So there are a bunch of clusters which don't look sensible, like the largest ones.
Mhm.
But the gradient similarity and average is also, I think, lower on those. And then things get more and more coherent. Like as they get smaller.
I think you meant low gradient, right?
Yeah, I meant, okay. But high similarity in the gradient direction is what matters more than the magnitude of the gradient.
Yeah, so I haven't like really systematically like clicked through and like looked at like how intuitively coherent the cluster is relative to like the average cosine similarity of the gradients. But that would be worthwhile. I would say like overall about so within the clusters, these are not cherry picked. So there was one sample in the new line cluster out of like 10 to 30, which was not predicting a new line. Like the others seem to be like predicting new lines for this reason. And then but some of the clusters are not very coherent, at least for an interpretable reason for us. Yeah. But they might have lots small gradients, but I'm not sure. Yeah.
You don't need any magnitude on this stuff?
No, but someone could do that. Yeah, you might like look at what parts of the model, like the gradients are most similar, like in, so maybe it's a particular block where like a lot of the similarity is coming from or something, and then you could try to do that. There is a direction in the embedding space that corresponds to the length of the token and like how many characters it has. Neil Nanda told me about this. So it's possible the model is like using this direction and like summing it up across a bunch of the tokens and then using that to like keep track of the line lengths and then that information. Yeah.
When you said that the other clusters were not so neat, were they not neat in the sense that there weren't like obvious like things like these all seem like very syntactic to me. It could be that the less neat ones are actually more deep.
Yeah, it's possible. I think it's a good idea to like look at the grade similarity. So when we do spectral clustering, you have to set the number of clusters ahead of time, and so everything has to be put in a cluster. And maybe if you chose a low number, then like it has to put a bunch of junk in the same cluster. Maybe if you had like much more data and many more clusters, like things would overall look more coherent. But yeah, it's a good point. Maybe there's just like some like very abstract reason why things are in the same cluster. Yeah.
I think this is a stupid question, but what are the objects that you're clustering, that you're feeding into the spectral clustering?
Yeah, so the like adjacency matrix, or like the similarity matrix that we give to the spectral clustering algorithm is, oh sorry, I didn't explain this. So it's the cosine similarities, so of the gradients. So we like evaluate the model at 10,000 samples, then we have 10,000 like very high dimensional gradients, and then we like compute the pairwise cosine similarity between all of these, and then that's what we give to the clustering algorithm. This is kind of expensive and difficult to scale.
Yeah.
Oh yeah, and then we're just curious whether like the size of the clusters follows the power law, and it's kind of messy. Like here, we're showing it for a bunch of different choices for the number of clusters in the clustering algorithm. And instead, like a bunch of the early stuff is probably junk, so we probably should have thrown it away when we were making this plot. But like here, we're showing the clusters ranked by their size against the number of elements in the cluster, and so this is a rank frequency curve, so it doesn't follow power law. I don't know, it's pretty messy. Maybe eventually it follows a power law. If you measure from like 100 to 1,000, you get the red line, which is a bit steeper than what we would have expected given the like empirical scaling exponent. So we would have expected the at least under our model, the
Less
Like-
than one, right?
oh, well, I guess here you so if the alpha is like 0.8 or 0.1 or something, then the frequency exponent is like
Oh.
1.1.
Yeah, okay.
So like it's a little bit steeper by 0.1 or something.
What happens at the end? They seem to drop off when I was baptized.
Oh, yeah. Well, like if there are only 400 clusters, then oh, why did they drop though?
It's a finite size effect because the
Yeah.
length is,
I think so, yeah.
so I should be more.
Yeah. Okay, and I'll just hit some last things. So reasons why we should be maybe really skeptical of the story. Number one, here are a bunch of empirical scaling exponents across studies of neural scaling, where people measured the scaling on their data with respect to n and with respect to a number of data points. So here's Kaplan, OpenAI, here's Chinchilla, there's a bunch of other junk. And overall, this is really messy. I think maybe we should trust Chinchilla the most, and it's like right between the line that we would expect from some other models of neural scaling, where the parameter and data exponent is the same, and ours, where it's a little bit different because there's this like alpha over 1 correction thing going on, and it's like right in between them. So yeah,
Oh, I mean, so some of them are completely off.
yeah, I don't know what's going on here. Also, super weird that both of these were language modeling papers and studies, and like the scaling exponents were so much shallower for OpenAI than DeepMind. So like what changed? I don't understand this. Like, I don't know if any existing models of scaling can explain this, because like, what is different about the data? Like, did the manifold dimension change? Really what changed was they were doing optimization in a different way.
And
Right.
the other are like vision, they don't correspond to language.
Yeah, I think some of these are vision. This might be specifically translation. This might be audio, but I forget. Yeah.
Trying to understand how to make the scaling exponents go that way seems like a bad thing to do, doesn't it?
Yeah. Well,
Like
I mean, I didn't do that.
Yeah. But let's not try and,
Sure. Yeah.
sorry.
Yeah.
But your model is supposed to be somehow universal, right? So you're basically saying this model only fits language.
Yeah, but there could be like different mechanisms of power law scaling, where like for some data, like the kind of smoothly, globally better approximating a function on a manifold story might just like be the actual story. And then like scaling exponents come from the manifold dimension. But then if you instead have this power law over discrete things, then it comes from the power law exponent for the frequencies. And then like maybe there are other models.
Yeah. So it's like critical to them.
Oh yeah. Sorry, I'm kind of cutting into your.
That's fine.
Okay. Yeah, so there's this other problem, which is that like what would the joint parameter data scaling law be here? I think like the story that I gave for like how increasing number of parameters, increasing amount of data allows you to learn more quanta, like suggests a kind of like hard bottleneck, which you can be independently bottlenecked by either. And so I think that you would expect maybe a joint parameter data scaling law that looks like this, like max of like, you can either hard bottleneck by this or hard bottleneck by that. And it's just like whichever one you're bottlenecked earlier by, that's your loss. But like in practice, people can trade off, I think, between training a bigger model for less time on less data and a smaller model for more time. Like people have lately, I hear have been training like smaller models for more time because it's cheaper to do inference, even if it's like more costly to do the training run. And like it seems like being able to do this trading off between data and parameters is not really a property of this model. So I don't know what's going on. Maybe like there's this optimization story you could come up with for like how many things you learn and like the effect that increasing the size of the network has. how many things to learn. But anyway, this is another problem. Yet another problem is that it seems like large jumps in the loss are kind of rare. So if we look at in the Python sequence, the distribution over changes in the loss on individual tokens when you move from one model to the next model, it's like the next biggest model. Like, well, does that consist of like a small number of large changes or like a large number of small changes? And it feels like this, well, here's like the density over changes from like doubling model size in per token losses. And like changing not at all is super common, but maybe this is like because the model is just like at 0 and it's like continuing to get 0 loss on a bunch of easy tokens. But then like you might see that like, oh, well, dropping by 2 bits is like 100 times less common than dropping by like a very small amount. So it's like, well, are there a bunch of discrete changes? Like this feels more of like a smooth, like it's a bunch of randomness and
At least per token.
at least per
It
token.
doesn't, yeah. Tokens are like definitely the easiest way to break it up, but they're not necessarily the correct way to break it up, right? And then like the thing Quentin said before about if the discrete quanta are like across tokens, then you expect tokens to do as much more of a very smooth thing, right?
So if like the this like discreteness is like not like aligned with like actual like sub problems in like tokens,
Then like if this token is involved in like 100 tasks and only one of the 100 tasks has a dramatic drop, then we expect a very small drop in the performance of the token, of the loss of the token.
Right. So maybe there's still some discreteness. It's just that everything or like most things are very like what we would call polygenic. It's like a large number of the quanta involved in prediction.
Isn't it like actually the case that the majority of individual tasks we've tried demonstrate emergence as model scales increase? I feel like I remember someone compiling them and getting like 70%.
Yeah, I remember a tweet from Jason Way. And he had a pie plot of like the fraction which he thought were like unpredictable and emergent versus like smoothly increasing versus something else. And I don't remember exactly the fraction that were emergent, but it was I don't know, like 30 to 70%, but I don't remember what it was.
Yeah, so
maybe that was it.
yeah, so maybe if you like do separate things by the task implied by the prediction rather than the token of the prediction.
Yeah.
You do get the loftiness.
Yeah.
Or at least you're not like 100 times less likely to get loftiness than smoothness.
Yeah. Yeah, maybe. It would be great if there's some automatic way to figure that out. Like ultimately you would want to find some like change internally in the model. Maybe rather than like relying on like having the right benchmark. But like I don't know exactly how to do this. Like you could like look for large changes in the weights, but like maybe like not that much has to change in the weights very quickly or something. Like for there to be a significant change in the model's output, depending on like where it is in the model and parts flying together and starting to interact in a good way.
Yeah, I guess the gradient clustering thing from before they kind of do this automatically.
Yeah, so like for the samples in the cluster, you could look at how their mean changes over time. But I guess like these, because the loss is like so low, I like sort of expect them to be more monogenic. And like I'm still not exactly sure what to do with polygenic stuff.
Yeah, so maybe like look for those results in the biggest models and then see how the corresponding specific predictions evolve in the smaller models, something like that.
I think we've moved into question time. Let's make sure you get through any remaining slides.
Nope. Thanks.
Okay. More questions for Eric?
Do you have any plans for corrections, more realistic versions of this Any assumptions you'd like to relax?
There's the assumption that like everything reduces the loss by the same amount. You could instead say that like it reduces it by an amount. There's some distribution governing the amount that it decreases it by, and then like if it's independent, then that distribution has a mean, and then like what's going on might have like more variance or something, but like you might still be able to the point.
And what about the Q model, the Q sequence? Or like,
Oh,
like double descent shows that models sometimes don't learn things in an unoptimal order. Epoch-wise double descent.
Oh, yeah, like there could be some noise in like which thing to learn. And like, rather than it just being exactly in order, there could be some probabilistic, like, yeah, like, if you have this number of parameters, then this gives you a probability distribution over which quanta are there. And then like, as you increase the number of parameters, you have a different probability distribution, which any sample from when you train.
What have you? Is there much to say about what kind of things you can do with the quantum model apart from scaling law stuff? Or do you think it's built specifically to try and understand scaling laws?
I guess you might hope to like eventually automatically like discover a bunch more language model behaviors in the way that we did, and then like automatically try to mechanistically understand them. And then like the hope was maybe you'll be able to just like automatically enumerate this like set of capabilities that like all models should have, and then like for each one of them understand like how it's implemented, and like maybe it's the same across scales, and then like you could just automatically do a bunch of capability or something.
How does the quanta view maybe feed into that?
Well, okay, so there are other models of scaling where like, you're just really approximating some function. But like, it's kind of unclear in that case, like what the right objects to study would be maybe for doing interpretability. Like it's very general kind of theory. So here it's like there just are objects, which like we are saying are like the right objects for understanding the performance of the network for these quanta. And like, I don't know exactly what they are. Like, if there's like, is it that networks learn more features, or that they learn more circuits?
It's like not constructive, right? It's
Some. And like, it'd be good to know what the functional unit was. I guess like it's the quanta, but like, that doesn't help you really. So, yeah.
It seems like a lot of the hard work is in identifying this quanta. But
Yeah, but like maybe, like they correspond to these behaviors that have similar gradients.
Yeah,
and
yeah.
You could like match doing this for models of different sizes and different seeds, and like, oh, how universal are they, and like how are these implemented, and how they change over time. Like it kind of does provide some framework for trying to understand like the whole model. It's like these are the parts, and here's how they form, and here's like what models they're going to form, and so on.
First, you have to believe they exist
Yeah.
before you go looking.
Is there some theoretical argument, or even if hand waving, why you would believe that this quanta exists?
So I guess in the several months before I was working on this, I was thinking about grokking and like networks trained on algorithmic tasks. And like here you see maybe more learning curves that look like phase transitions. And so then there was this like hypothesis in Neil Nanda's grokking work, like maybe these phase changes are everywhere, and like the paper and like they're just really small, and so like smoothness is averaging over lots of phase transitions. And like yes, it's like it's possible for learning curves to average over lots of phase transitions. In the parity example, maybe.
Because I mean, somehow my intuition about phase transition is sort of the opposite, but at the phase transition, you see long-range behavior, right? This is a typical understanding in the theory of critical phenomena, that long-range fluctuations, right? Effective theory of the transition, they dominate. So it's, if there's any kind of quanta, right, they should be quanta of those fields that appear at this transition. But each transition has its own universality class. That's the expectation from physics. So you should have these different types of quanta. So you'd expect a very complicated wealth of such things, which doesn't fit your simple model. And that's somehow intuition based on physics. If you
Yeah.
take this analogy to phase transition series.
Yeah, I don't think that there's like very strong empirical evidence right now, for this model or that, like, there's state changes everywhere in language model.
Okay, thanks.
All right. Yeah.
This isn't a question for you. It's a question for you. What sorts of